Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics, 3, RLT College of Science, Akola. Dear student, in a previous lecture we have seen model number 3. Okay, so in this lecture we will see model number 4, that is generalized model, or it is called as a birth-death process model. Okay, so before going to start this model, we will see what is the generalized model. Okay, so this model this with the queuing system having single service channel, so which is a Poisson input with no limit on the system capacity. So in this birth death process, the arrivals can be considered as a birth to the system, whereas the departure can be considered as a death. Okay, so let us we consider some notations for this. The model number 4, where n is the number of the customers in the system. Lambda n is arrival rate of the customers given in n customers in the system. Mu n departure rate of the customers given n customer in the system, and Pn means steady state probability of a n customer in a system. Okay, so this is the model number 4, that is birth death process model. So the model determines the values of the Pn in terms of lambda n and mu n. Okay, so by using the axioms of the Poisson process or distribution, we observe that the arrival during the small time interval delta is negligible. Okay, so this implies that for n greater than 0, state that n can be changed only to possible stated. So for state n minus 1, when a departure occurs at the rate mu n, and a state at n plus 1, when an arrival occurs at a rate lambda n. Okay, so but actually at a 0 state, so state 0 can only change the state when arrival occurs at the rate lambda 0, because no departure is possible when the system is empty, mu 0 is undefined. Okay, so let us we consider the steady state conditions for n greater than 0. Okay, the rate of flow into and out of the state n must be the equal. So this illustrates the transition rate of the following diagram. So this is the transition state of the following diagram. Okay, so now we will see the equations, a difference equation, or we can say the balance equations of the this model number 4. The expected rate of flow into state n equal to expected rate of flow out of n state, and it is mathematically can be written as lambda n minus 1 into Pn minus 1 plus mu n plus 1 Pn plus 1 equal to lambda n Pn plus mu n Pn. Okay, for n greater than equal to 1, and for n equal to 0, then mu1 P1 equal to lambda 0 P0. Okay, so we will find out the solution of this model number 4. So by using the same procedure of the model number 1, which we have already discussed in, I think, second lecture or second or third lecture. Okay, so by using the model number 1 and using the iterative procedure, we can obtain the term, that is P1 equal to lambda 0 upon mu1 P0, P2 lambda 1 plus mu1 upon mu2 P1 minus lambda 0 upon mu2 P0, so which is equal to lambda 1 lambda 0 divided by lambda 2 mu2 mu1 into P0. So similarly we can find out P3, that is lambda 2 plus mu2 upon mu3 into P2 minus lambda 1 upon mu3 P1, and which is can be written as, by using the values of P1 P2, we will get lambda 1 lambda 0 lambda 1 lambda 2 divided by mu1 mu2 mu3 into P0. Okay, so in this way we can find out the uh, uh, balance equation or steady state equation P1, P2, P3, P4 and so on up to. Okay, so by using this procedure or in this manner we can write the general formula, that is Pn equal to lambda n minus 1, lambda n minus 2, lambda and dot 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 lambda 0 divided by mu n minus 1 and so on mu 1 p0 for n greater than equal to 1. Okay, or this can be also written as, so by Pn equal to p0 product of I equal to 0 to n minus 1 lambda I upon mu I plus 1 for n greater than equal to 1. Okay, now for the n plus 1 term we can write Pn plus 1 equal to lambda n plus mu n divided by mu n plus 1 Pn minus lambda n minus 1 divided by mu n plus 1 Pn minus 1. So by using the values of P1, P2 and so on, so we can read as P0 product of lambda I upon mu I plus 1 I have from 0 to n. Okay, so by the mathematical induction method, okay, so by using the mathematical induction method, the general value of the Pn holds for all the values of n. Okay, now we will obtain the values of P0. So to obtain the value of P0 we use the boundary condition, and the boundary condition is given as summation Pn equal to 1 where n varying from 0 to infinity. So this also can be written as P0 plus, this can be written as P0 plus summation n equal to 1 to infinity Pn equal to 1. Okay, so to get P0 equal to 1 plus summation product I varying from 1 to infinity I varying from 1 to n minus 1 lambda upon mu I plus 1 to the power minus 1. Okay, so this is the model number 4. Now we will see some special cases for this model. So case number 1, when lambda n equal to lambda for n greater than equal to 0 and mu n equal to mu for n greater than 1. So which implies P0 equal to 1 plus summation n equal to 1 to infinity lambda by mu to the power n power minus 1, and this can be written as, that is 1 minus rho. Okay, so in this case we can write, that is Pn equal to rho to the power n 1 minus rho for n greater than equal to 0. Okay, so therefore this result is exactly the same as the model number 1. Case number 2, when lambda n equal to lambda divided by n plus 1 for n greater than equal to 0 and mu n equal to mu for n greater than 1. Okay, then P0 can be found to be, so by using this simple calculations we will get e to the power minus rho. Okay, so therefore here Pn equal to 1 upon n factorial rho to the power n e raised to the power minus rho for n greater than equal to 0, and here rho is lambda by mu. Okay, so which we already discussed in model number 1. So which is the Poisson distribution with a mean E of n equal to rho. Now we will discuss case number 3, when lambda n equal to lambda for n greater than equal to 0 and mu n equal to n mu for n greater than 1. So here we will find out P0 equal to 1 plus summation n equal to 1 to infinity lambda n upon n factorial mu to the power n power minus 1, and this can be written as e raised to power minus rho, and we know that rho is lambda by mu. So therefore here Pn equal to 1 upon n factorial rho to the power n e raised to power minus rho for n greater than equal to 0. Okay, for the value of rho equal to lambda by mu. Okay, so this will give the again Poisson with mean E of n equal to rho and E of m equal to 0, E of w equal to 0. Okay, so in this case the service rate increases with increase the queue length, and hence is known as the queuing problem with the infinite number of channels, that is m infinity infinity, first in first out. This model is known as a self-service model. This model is also known as a self-service model. Okay, so this is the model number 4, that is birth death process model, or it is called as a generalized model of birth and death process. Now we will see the one example on this model. What is the example? Problems Problems arrive at a computing center in a Poisson fashion at an average rate of 5 per day. The rules of the computing center are that any man waiting to get his problem solved must out the man whose problem is being solved. If the time to solve a problem with one man has an exponential distribution with a mean time of 1 by 3 day, and if the average solving time is inversely proportional to the number of the people working in the problem, approximate the expected time in the center for a person entering the line. Okay, so this is the one example on a generalized model. Okay, so first we will write down the given data in the form of mathematical symbols. Okay, so if you observe here, lambda is given as problems per day, that is lambda equal to 5. Okay, and also here we have given mu problems per day, that is 3, that is lambda by mu, that is lambda by mu is 1 by 3, that is mu equal to 3 problems per day. So this given as the service rate increase with the increase in the number of persons, that is therefore mu n equal to n mu. So here n is a there are n number problems, and Pn equal to 1 upon n factorial rho to the power n e raised to power minus rho. Okay, so now expected value of n equal to summation n equal to 0 to infinity n Pn. So this can be written as putting the value of Pn, that is summation n equal to 0 to infinity n 1 upon n factorial rho to the power n rho to the e to the power minus rho. So we will get e to the power minus rho e to the power plus rho. Okay, so this will get cancelled, so only remaining here, that is rho, and that is rho is, that is 5 by 3, that is 5.63. Okay, we know that lambda is, that is rho is lambda by mu. So by using formula lambda rho equal to lambda by mu, that is 5 by 3, that is 1.67. Okay, now the average solving time, which is inversely proportional to the number of people working on the problem, is given by 1 by 5 day per problem. So therefore the expected time for a person entering in a line, and which is given by 1 upon 5 expected of n. Okay, so here we have find out expected of n, that is 5 by 3 per day. Okay, so putting the values of e of n from this equation, so we will get 1 by 5 into 5 by 3 days, that is equal to 1 by 3 day, or we can say that 8 hours. Okay, so this is in the form of day and this is in the form of hours. Okay, so therefore expected time for a person entering in a line will be the 8 hours. Okay, so this is the one simple example on a generalized model, that is called as a birth death process model. Okay, so dear student, in next lecture we will see model number 5, model number 5. Okay, and we will see some problems on model number 5. Okay.